Hi, my name is Laura Carending, and I will be doing a screencast on coordination compounds. Transition metals are typically what form coordination compounds. These compounds are usually colored and they are often paramagnetic. A coordination compound typically consists of a complex ion, which is a transition metal ion with its attached ligands, and counter ions, which are anions or cations that are needed to produce a compound with no net charge. Here is an example of a coordination compound. This one right here. So when this is dissolved in water, the solid behaves like any ionic solid, where the cations and the anions are assumed to separate and move about independently. This is a typical coordination complex, and in this you can see that there are square brackets here, and these square brackets indicate the composition of the complex ion. And outside, over here in this area, are the counter ions. Here's a little bit of the history of coordination compounds. So they have been known since about the 1700s, but they were not truly understood until the 1890s, when Alfred Werner proposed that transition metal ions have two types of valence, or combining ability. And this is a picture of Alfred Werner over here, and he was a Swiss chemist. He proposed that there were two types of valence: the primary valence, which is the ability of the metal ion to form ionic bonds with oppositely charged ions, which is now known as the oxidation state, as well as the secondary valence, and that is the ability of a metal ion to bind to Lewis bases to form complex ions, which is now known as the coordination number. And down here in this corner is Gian Lewis, who is responsible for the Lewis base definition and Lewis acids. The coordination number varies from 2 to 8, and it depends on the size, the charge, and the electron configuration of the transition metal ion. And the most common coordination number is 6, and that's followed closely by 4, and some metal ions show a coordination number of 2. There isn't a simple way to predict the coordination number, but there are typical geometries for the different common coordination numbers. So earlier we talked about ligands, and you may be wondering, what is a ligand? So a ligand is a neutral molecular ion having a lone pair that can be used to form a bond to a metal ion. And in the 1920s, Gian Lewis suggested a different definition for acid-base behavior, and he did this by defining them in terms of electron pairs. So an acid he defined as an electron pair acceptor, and a base he defined as an electron pair donor. And so you can look at ligands differently, because ligands donate an electron pair to an empty orbital on a metal ion, so this would be seen as a base in Lewis's definitions. And so the types of ligands, there are a few types. There's the monodentate ligand, which is also known as unidentate. There's the chelating ligand, the bidentate ligand, and the polydentate ligand, and we'll go over that in the next slide. So a monodentate ligand is a ligand that can form one bond to a metal ion, and the word monodentate has root words meaning one tooth, and it's often seen that a ligand bites a metal, so literally that's what you can think of it as, and in this case it would only bite it once. So here's a joke. What did one metal say to a ligand in a coordination compound? Stop biting me! There are other types of ligands, and some of them have more than one atom with a lone pair that can be used to bond to a metal ion, and these are called chelating ligands, and the word chelate comes from the Greek word chela, meaning claw. And so this is another type. And another type is bidentate, and that's a ligand that can form two bonds to a metal ion. And a common one of this is ethylene diamine, abbreviated EN, and that's just one type. Another type is oxalate. So here I drew for you oxalate in red, and in green ethylene diamine, and you can see here that the ligand can form 2 bonds to a metal ion. Ligands that can form more than 2 bonds to a metal ion are called polydentate ligands, and some ligands can form as many as 6 bonds to a metal ion. And the best known ones are ethylene diamine etracetate and diethylene triamine, and these are the abbreviations here. And I'll draw some diagrams for you guys. So here are EDTA and DN drawn out. So this one is DN here, and there are 3 coordinating atoms, and you can see the lone pairs here, and these are the coordinating atoms that make it polydentate. And in EDTA, over by the oxygens, and as well as the nitrogen, here's some arrows that are pointing out the coordinating atoms, and there are 6, so it's clearly polydentate. When the coordinating number is 2, the geometry is typically linear. When the coordination number is 4, then it can be tetrahedral or square planar, and when the coordination number is 6, it is the octahedral shape. So during Alfred Werner's lifetime, there was no system to name these coordination compounds, and they were usually based on colors and names of discoverers, but as the field grew and more coordination compounds were discovered, then they developed a nomenclature system, and here are the rules. So, like any ionic compound, the cation is named before the anion, and in naming the complex ion, you name the ligands before the metal ion. In naming ligands, an O is added to the root name of an anion. So, for example, in halides, the ligands are called fluoro, chloro, bromo, and iodo, and hydroxide is hydroxo, and cyanide is cyano. And if the ligand is neutral, then the name of the molecule is used. And there are exceptions to this, though: H2O, NH3CO, and NO. And another rule is that the prefixes mono, di, tri, tetra, penta, and hexa are used, and these denote the number of ligands. And for more complicated ligands that already contain di, tri, and the other prefixes, or if they're just more complicated, then you use different prefixes, and they are listed here. And so for the oxidation state, the oxidation state of the central metal ion is designated by a Roman numeral in parentheses, and when more than one type of ligand is present, ligands are named in alphabetical order, and the prefixes do not affect the order. And if the complex ion has a negative charge, then the suffix -ate is added to the name of the metal, and sometimes there are Latin names used to identify the metal. For example, for iron, there's an anionic complex base named ferrite, copper is cuprate, lead is plumbate, silver is argentate, gold is aurate, and tin is stannate. So those can also be used to identify the metal. Thank you so much for watching!